Good morning. Today we are going to discuss about electrophilic substitution reaction. Myself, Ravi Kumar, Associate Professor, Department of Pharmaceutical Chemistry, Nalla Narasimha Reddy Education Society, Group of Institutions, Hyderabad. Today we will discuss about electrophilic substitution reaction. The objectives of today's class is, at the end of class, students able to explain the electrophilic substitution reaction of benzene, why benzene undergoes electrophilic substitution reaction rather than addition reaction, predict the mechanism of electrophilic substitution reaction, able to write the halogenation, nitration, and sulfonation reactions with mechanism. Coming to the electrophilic substitution reaction, benzene undergoes electrophilic substitution reaction and it is resist to addition reactions and oxidation reactions. Now the question comes, why benzene undergoes electrophilic substitution reaction? Though benzene is having 3 pi bonds, it should have the properties of alkenes. So alkenes, the characteristic reactions are addition reactions. So benzene should undergo addition reactions, but benzene is not undergoing addition reaction, but it is undergoing electrophilic substitution reaction because of delocalization of electrons from one carbon to the other carbon. So because of delocalization of electrons, the electron system is rich. If you see this structure, all the carbon atoms are shifting the electron cloud from one carbon to other carbon, so that when the electrons are moving around the carbon, there is an electron cloud formed above the plane and below the plane. That is the reason benzene is a rich electron system. So benzene is acting as a nucleophile. It is a negative charge species. So because of that, benzene is not undergoing addition reaction. If it undergoes addition reaction, there is a disturbance in the electron cloud system or aromatic system. So benzene is a strong aromatic in nature, so it will not undergo addition reaction. Rather, it will undergo substitution reaction to protect the aromaticity. So what type of compounds do attack the benzene? So when benzene is a negative charge species, so the positive charge species should attack the benzene. So what type of positive charge species should attack? So here the electrophiles are the species which have positive charge, which are deficit of electrons, such as nitronium ion, chloronium ion, bromonium ion, and sulfonium ion. These are the electrophiles. Whenever they are reacting with benzene, then there is a chance of undergoing electrophilic substitution reaction. So benzene is acting as a nucleophile and it is being attacked by the electrophiles. Benzene is an electron rich species and the electrophiles are electron deficient species. If you see the basic reactions of electrophilic substitution reaction, benzene, when it is reacted with an heterogeneous compound which has an electrophile and nucleophile. For example, if you take alkyl chloride CH3Cl, CH3Cl, when it undergoes a electrolytic fission, it forms CH3 plus and Cl minus. Or if you take acetyl chloride, CH3 C double bond O Cl, when Cl is going out of the substrate, it forms acetyl group CH3 C double bond O. Right? So this is a heterogeneous compound. So when benzene reacts with this heterogeneous compound in the presence of a catalyst, why we need to use a catalyst? Because benzene is a strong or stable compound. It is resistant to any reaction. But when you are adding a catalyst, this prompts benzene to go for the reaction. It increases the rate of reaction. Catalyst is very important for benzene reactions. So when benzene is reacting with heterogeneous compound in the presence of a catalyst, it gives rise to a substituted product because it is not undergoing addition reaction, so it is undergoing substituted product. Why? Because electrophile is being attacked, so electrophilic substituted product is formed with the release of nucleophile with hydrogen, because this hydrogen is coming from benzene, because hydrogen is replaced with of electrophile, so this is a substituted product. What would be the mechanism of reaction? In the mechanism of reaction, we have three steps. One is formation of electrophile. How an electrophile is formed? When a heterogeneous compound is reacted with a catalyst, it undergoes electrolytic fission such that E will lose electrons and nucleophile will gain electrons, so that it forms N minus, nucleophile negative charge, and E positive charge. E positive charge we call as electrophile, and nucleophile will combine with the catalyst to form a complex. Whatever the electrophile which is formed, that will attack the aromatic ring to form a carbocation. Carbocation. What do you mean by carbocation? And a species which has a positive charge compound. Carbon bearing positive charge we call as carbocation. So when benzene is reacting with electrophile, so benzene is, we know that it is a electron rich species. This attacks electrophile, means benzene is donating electron charge to the electrophile, so that this carbon is getting positive charge. So if you see this carbon is getting positive charge, so carbon positive charge species we called as carbocation. The carbocation which is formed is not staying on this carbon itself, because we know that benzene is a resonance stabilized compound, so there is a possibility of delocalization. So this carbocation, when it loses, when the pi bond, to nullify this positive charge, the pi bond shifts here to form a bond with this carbon, such that this carbon loses electrons, so it gets positive charge. So shifting of pi bond takes place from one carbon to other carbon, so that the third para carbon becomes positive. To nullify this positive charge, again the pi bond shifts here, so that profile carbocation positive charge is formed here. Means the positive charge is not idle, it is shifting from one carbon to other carbon, and it is rotating like this. So this carbocation, which is a resonance stabilized form, it forms three hybrid structures like this. So whatever the positive charge which is formed is stabilized by this carbon to form another positive charge, which is being stabilized here to form this positive charge. Once the stabilized resonance stabilized carbocation is formed, this next step is loss of proton. Whatever the proton, because when this molecule is unstable, because we know that benzene is aromatic nucleus, means complete conjugation is there and delocalization will take place, but there is a disturbance in aromaticity, because you have only partial alternate double bonds, but here the carbon is not having double bond. So to regain the double bond, whatever the carbonium which is there will react with a complex, nucleophile catalyst complex, that will attract this proton. The nucleophile which is there attracts the proton, such that the proton is lost and it forms Nu nucleophile H, and catalyst is formed. Once it is formed, the pair of electron which is there will shift to the aromatic nucleus, because this pair of electron, hydrogen is going as H plus, so the pair of electron which is there will enter into the pi system to nullify this positive charge to form a aromatic compound. So you got the substituted product. So if you see the energy diagram of electrophilic substitution reaction, so benzene, when it is reacted with electrophile, it needs energy. It needs energy such that it can combine each other to form a transition state. Step one, this transition it needs EA1 energy such that it forms an intermediate. It forms an intermediate. This we have seen, when the intermediate is there, there is a partial positive charge all over the carbon ring. So to form the starting compound to intermediate, it needs transition state energy, that is EA1. It is high and it's very slow. The reaction is very slow, means reaction with the benzene and electrophile is very slow. Why? Because we have benzene that is more stable in nature. So when benzene is reacting with electrophile, the reaction is very slow. It needs EA1 energy such that you got the intermediate. Once the intermediate is formed, this intermediate, when it is reacting with a base, again the base accepts a proton, and the aromaticity, the electrons will shift to the aromatic ring, and this reaction is very fast, and it needs only less energy of transition state. So once the reaction is done, so it gives a stable product. When you compare here benzene and substitute benzene is more stable and have less energy than that of benzene. So definitely the reaction is not reversible. So what happens? It has benzene reacts with electrophile to form intermediate compound, which is unstable and which loses high proton to form aromatic nature back to form a substituted product. Means hydrogen is being replaced with the electrophile to form a substituted product. This is about energy diagram of electrophilic substitution reaction. So now come to the halogenation reaction. What do you mean by halogenation? Addition or substitution of halogen with a benzene, or introducing a halogen to the benzene ring is called halogenation reaction. So benzene reacts with a chlorine in the presence of a Lewis acid, that is FeCl3 or AlCl3, ferric chloride or aluminum chloride. So these Lewis acid which accepts a pair of electron. So these are acting as a catalyst at a room temperature. So benzene reacts with chlorine in the presence of this Lewis acid, say ferric chloride or aluminum chloride. Room temperature gives chlorobenzene. Right. So sometimes you can use iron powder also instead of ferric chloride. So when benzene is reacting with the chlorine molecule, so in the presence of FeCl3, you get chlorobenzene and HCl is formed. Means hydrogen from benzene is substituted with the chlorine atom, chlorine free radical, chlorine electrophile, that is chloronium ion, and one of the chlorine and hydrogen is formed as HCl. So if you see the mechanism of reaction, formation of electrophile, that is chloronium ion. So chlorine molecule, we know that it is a covalent bond. When it is reacting with ferric chloride, FeCl3, here iron is getting three positive charges, and because it is attached to 3 chloride anions, oxidation state of iron is 3. And when ferric chloride is reacting with this, we know that iron is electropositive. It attracts the chlorine. So it attracts the chlorine along with its pair of electron. So this bond breaks, a chlorine molecule bond breaks, and the pair of electron which is there between chlorines will go to the iron and forms tetrachloroferrate. That is, chlorine is having 4 chloride anions, and iron is getting a negative charge now. So once the pair of electrons are lost to the ferric chloride, now this chlorine ion is deficit of electrons, and it forms chloronium ion or chlorine positive charge. We call it as chlorine cation. This is an electrophile. Now this chlorine cation, which is electrophile in the solution, will try to attack the benzene ring. So chlorine cation attacks the benzene ring to form a carbocation. We have seen in the general reaction. Now benzene, when it is reacted with chlorine cation, the benzene is electron-rich species, will try to donate electron to this chlorine atom so that it forms a carbocation. So positive charge is formed. Why? Because the pair of electron is donated to chlorine. So it forms, this carbon gets positive charge, and this carbon is resonance stabilized. The positive charge which is formed in the carbocation is been nullified such that this carbon get positive charge. Once the carbon get positive charge, the delocalization takes place. The pair of electrons will shift to the next carbon, positive charge carbon, so that this carbon gets positive charge. So it is a resonance stabilized carbocation. Once this resonance state carbocation is there, that will react with a base which is there in the solution. The third step is loss of proton to yield chlorobenzene. What exactly happens here is the carbocation which is there will react with the base which is formed, that is FeCl4 minus. The FeCl4 minus will react with abstract the proton from benzene structure carbocation. So when it abstracts the proton from benzene carbocation, so it forms HCl. This chlorine atom will abstract the proton to form HCl, and reagent catalyst is generated. Again, regenerated catalyst is formed, and the pair of electrons which are there between carbon and hydrogen will enter into the pi system to form chlorobenzene. So this is about halogenation reaction. Coming to the bromination, same, it acts similarly. Bromine reacts with benzene similarly to form bromobenzene. So bromine, when it is reacted with the bromine molecule, benzene react with the bromine molecule in the presence of ferric bromide, it gives rise to bromobenzene and HBr. Coming to the nitration reaction, benzene, when it reacts with nitration mixture at 60 degrees centigrade to form nitrobenzene. So here nitration mixture is nothing but it is concentrated HNO3 in the presence of concentrated H2SO4. These two acids combine to form nitration mixture. So when benzene is reacting with nitration mixture at 60 degrees centigrade, it gives rise to nitrobenzene. So benzene, when it is reacted with concentrated HNO3 in the presence of concentrated H2SO4, gives rise to nitrobenzene, and nitration mixture we call as concentrated HNO3, the nitric acid, in the presence of concentrated H2SO4. So mechanism is similar with that of previously explained formation of electrophile. So in nitration reaction, the electrophile is a nitronium ion. Nitronium ion is a nitro group with positive charge. We call it as nitronium ion. Nitro plus onium ion. Onium ion is nothing but positive charge, nitronium ion. So whatever the nitronium ion is formed, how it is formed? When nitric acid reacts with sulfuric acid. So here sulfuric acid, we need to take excess concentration, excess amount of nitric acid sulfuric acid should be taken in the ratio of 2:1. When more amount of sulfuric acid is there, this sulfuric acid is acting as a acid, it donates proton, so that nitric acid try to abstract the proton from acid to form OH2 plus. OH2 is formed here. H is donated to this OH to form OH2, which is unstable. So that this OH oxygen, we know that it is positive charge. Oxygen positive charge means it is very, very unstable. It will try to get the pair of electron from the neighboring atoms or bond. So when it what exactly happens, this becomes more electron withdrawing group, so it will try to pull the electron cloud. The oxygen minus which is there in the nitro group will form the resonance structure. The O minus will form a double bond, such that the pair of electron which is there, bonding electrons will shift to the oxygen to get water molecule. The water molecule is formed here, and nitrogen becomes a nitronium ion. This is very electron deficient species, that is electrophile nitronium ion, which is there, will react with benzene. Now the second stage is, second step is nitronium ion, which is formed in the reaction when concentrated sulfuric acid and nitric acid reacts. So that will attack the benzene ring to form carbocation ion. So again, benzene, when it is reacted with nitronium ion, the nitronium ion is electron deficient species. It needs electrons. Benzene is having more electron cloud, and it donates electrons to the nitronium ion, so that carbon becomes benzene ring becomes carbonium ion again now. So this is a carbonium ion state, which is intermediate state, and it undergoes a resonance stabilization. So this is a carbonium ion form, and it undergoes delocalization to form carbonium ion again. So this is stabilized rings for carbocations. Once this is formed, this carbocation will react with base which is formed in the solution. So loss of proton yields to the nitrobenzene. So the carbocation which is reacting with a base, what is this base? Because of sulfuric acid donate a proton to form a base. So conjugated base is formed, weak conjugated base is formed. This which conjugated base abstracts a proton from benzene. So it abstracts a proton from benzene, so that it forms H2SO4 is formed back in the solution, and the pair of electrons which are there will go to into the pi system to form nitrobenzene. So the nitrobenzene is formed here. And another reaction we can see here, sulfonation reaction, where the sulfonyl group is attached to the benzene ring. Means benzene react with fuming sulfuric acid or excess of concentrated sulfuric acid to give benzene sulfonic acid. So when benzene, when it is reacted with sulfur trioxide in the presence of concentrated H2SO4, we call it as fuming sulfuric acid. Means sulfur trioxide is acting as electrophile. Sulfur trioxide, when it is reacted with concentrated sulfuric acid, So it forms, it generates an electrophile. When it attacks the benzene, it gives rise to benzene sulfonic acid. Another type of reaction is there, that is benzene. When it is reacting with excess of concentrated sulfuric acid, it also gives a benzene sulfonic acid. So the mechanism here is the formation of electrophile, that is sulfonium ion. How sulfonium ion is formed? The sulfur trioxide, we know that sulfur is electrophile in nature, but sulfur is why electrophile? Because sulfur is attached to 3 oxygens. So oxygens being electron negative charge, so it will try to pull the electron cloud from sulfur. So now sulfur is electropositive and electron deficient. If at all this sulfur is trying to get any atom, so it gets stabilized. So it forms, whenever sulfur trioxide is reacting with constant sulfuric acid, this constant sulfuric acid, the sulfur, it forms O minus. O minus attacks this proton, so it subtracts proton to form stable electrophile, that is sulfonium ion, and it gives rise to HSO4 minus is formed, because the proton is being accepted by a oxygen, and the bonding electrons which are there will go to the oxygen. Why bonding electrons are going to oxygen? Because oxygen is more electronegative. It will try to bring the electron back to the oxygen, and it forms HSO4 minus, and sulfonium ion is formed, that is electrophile. Or when constant sulfuric acid, 2 moles of constant sulfuric acid is reacting, so here the oxygen which is there will try to abstract the proton from another sulfuric acid, so that it forms O plus, OH2 plus is formed. OH2 plus is a best living group, we know that, but why it is a best living group? Because oxygen is positive charge, which is very unstable. We know that when oxygen is positive, it will try to get the pair of electron from its neighboring atom or neighboring bond. So when it try to take the pair of electrons, so it forms sulfonium ion, that is HSO4 minus, and water is formed, and a base is formed, that is HSO4 minus is formed. So SO3 plus SO3 H plus is formed, and also a base is formed. So why base is formed? Sulfuric acid loses proton to form HSO4 minus, and this proton is accepted by sulfuric acid to form onium ion. Onium ion loses water molecule to form sulfonium ion. Sulfonium ion is acting as nucleophile. In these 2 steps, we will get a sulfonium ion, which is there in the solution, will try to attack the electron rich species, that is benzene. So sulfonium ion attacks the benzene to form a carbocation again. So similar mechanism, when benzene reacts with sulfonium ion, a benzene acts as electron rich species, and sulfonium ion is acting as a electron deficient species, because sulfur is electron deficient. Sulfur valency may be 2 or 4 or 6, but here the sulfur valency is 5. Electron deficient sulfur is in search of electron cloud. So when this benzene is coming to approaching the sulfonium ion, so it start donating a pair of electrons like this. So when it donates electrons, carbon cation is formed, because this carbon is losing electrons, and it forms carbocation. When carbocation is formed, again there is a resonance stabilization. Carbocation is formed. We know that the pi bond, to nullify this positive charge in the carbocation, so it forms a delocalization. The pi bond shifts here, and this carbon gets positive charge. To nullify this positive charge, again the aromatic double bond is shifting to the next carbon, so that what happens, this carbon gets positive charge. So it is a resonance stabilized carbon is formed. Once this resonance stabilized carbocation is formed, this will react with a strong base which is formed in the solution. What is the strong base form? HSO4 minus. So it loses proton. Whatever the HSO4 minus which is there will try to abstract this proton. So to stabilize the carbocation. So HSO4 abstracts the proton and form H2SO4 back, and this pair of electrons which are there enter into the pi system, and delocalization takes place. So electron cloud is formed, gives rise to benzene sulfonic acid. So summary of the reaction, what we have seen, definition of electrophilic substitution reaction. Electrophilic substitution reaction is nothing but substitution of electrophile with a proton, substitution of a proton with another electrophile. So here benzene undergoes a substitution reaction because of delocalization of pi electrons. So though benzene is having a pi system, it should mimic the alkenes, but it is not mimicking alkenes because there is a delocalization of electrons. Means electrons are shifting from one carbon to the other carbon. There is electron cloud formed in the above the ring and below the ring. So benzene always undergoes electrophilic substitution reaction, and the general mechanism here we have seen. The student will able to write the mechanism of reactions and energy diagram. There are two energy transition states form. First reaction is very slow. It requires more amount of energy to form a transition state, and second energy is very less, and the transition intermediate compound is losing proton to form the substituted product. So energy diagrams we have seen, and we have seen the halogenation reaction to give chlorobenzene or bromobenzene, nitration reaction to give nitrobenzene, sulfonation reaction to give benzene sulfonyl sulfonic acid, and we have seen its reaction. So this is a summary of today's class, and the references are Arun Ball and D.S. Ball, organic chemistry, and Morrison Boyd, organic chemistry, and organic chemistry by I.L. Finnar. So in the next class, we'll see other reactions like free radical, Friedel-Crafts alkylation reaction, and rearrangement reactions of Friedel-Crafts alkylation reaction, and Friedel-Crafts acylation reactions, and some oxidation and addition reactions that we'll see in the next class. Thank you.